So we continue with now. We repeated some mathematics in the first hour, and now we have to repeat the physics or the basics, the fundamentals of electrical engineering. But first I have to correct a mistake. Before I made a mistake, I wrote phi here. Of course, it's 1r times 1 theta here, not 1 phi, but 1 theta. 1 theta, that's equal to 1 phi. So written in American notation, so unit vector r1 times unit vector in the direction of theta is a unit vector in the direction of phi. So I should have corrected this for the previous hour. Now, this hour we have to repeat electrical engineering, and we have to repeat the Maxwell equations. We are not going to make our life complicated because Maxwell equations relate to electrical quantities like charges, like electric field. But to simplify the relativistic problems, they don't use the theory of relativity, but rather they use magnetic quantities. And with Maxwell equations, I will first write them down the way you did at the fundamentals of electrical engineering 3 years ago. So the first law I'm going to mention here is the Gauss law. What does the Gauss law say? It says that integral over volume of the charge density, where charge density is a function of the position, but it's a scalar, and has units of ampere seconds per cubic meter. If I integrate over this volume, I have a total charge of Q. So if this is my volume, I have a certain charge density here, and maybe a function of the position. I get the total charge that's enclosed in this volume, total charge Q. But I can also compute this total charge from the vector, from the field of electric displacement. So if I integrate over the closed surface A, this vector of electric displacement D times unit vector, normal unit vector 1n, d surface. So unit vector is always defined to point out of the volume. So this is my unit vector 1n, and this is the surface A enclosing this volume V. I can also compute the total charge from the vector from the electric displacement field here. This is about the Gauss law. So now what is wrong with the Gauss law? Actually nothing. This thing holds. This is one of the basic laws of the 3 Maxwell equations. The problem here is the volume. This volume has to be a finite volume, not non-zero volume. And the surface, the closed surface that encloses this volume, is also non-zero. And when I have no zero quantities that involve dimensions, this is cubic meters, this is square meters, I do have problems with the special theory of relativity. So if something happens here, its effect on the other side is not immediate, but it's delayed. That's the theory of what the theory of relativity says. And this is makes our calculations very cumbersome. Also, maybe our calculations are incorrect. Now, this is the Gauss law, what I wrote here. This was physics. Physics is from here to here. But I have yet another Gauss law in mathematics. The Gauss law in mathematics says, so if I write here math, says that if I have such an integral, this integral can be transformed from surface integral to volume integral by a certain mathematical operation. And that mathematical operation is called divergence. Divergence, or density of sources of this same vector field, times differential of volume over the whole enclosed volume. This is the mathematical Gaussian theorem. And this function, we should be able to compute this function. What is this function really? This function, divergence of D, is really the density of the sources of this field, because the field, the electric field displacement D, has sources that are the charges. Mathematically, this is defined as differential operator Nabla, making a dot product over D, where Nabla, we are only able to write it in Cartesian coordinates. This is 1x partial derivative over x plus 1y partial derivative over y plus 1z partial derivative over z. We can make this definition of Nabla as long as these unit vectors, the base vectors of the coordinate system, are constant. This is not the case in the spherical coordinates, because in the spherical coordinates, if I go around the equator, if I go around the equator, around the Earth, my vector 1 east is the direction where longitude increases. It's changing its direction over the time. If it's changing direction, there exists a derivative of 1 east, and I cannot write Nabla in this way. So this is only valid in XYZ and nowhere else. Only that we know what we are talking about. And if I compare the rightmost side to the leftmost side, this is just, on the other side, this is just the charge density rho. So I could rewrite my total Gaussian law in differential format. So this was integral form. I have it here, and integral form suffers from these finite dimensions of the volume and of the surface. In differential form, the Gauss law simply states as divergence, so density of sources of the electric displacement is equal to the electrical charge density. This thing looks much similar, but don't forget what we have here. That's difficult to calculate. The real advantage of having a differential form is that this equation actually holds in every differentially small part of volume. We no longer need finite dimensions. We can squeeze these dimensions down to infinitesimally small, and this equation still holds. So this thing here is not affected by Einstein. It's not affected by the special theory of relativity. It has no power here, because we can make it arbitrarily small. And the Gauss law, this is all what we said about the Gauss law in differential form. We had our other laws in electrical engineering. For the three Maxwell equations, we also have the Ampere law. And we also have the Faraday law, Ampere law. What is the Ampere law? Ampere law, what does it say? It says that if I make an integral of enclosed curve, of the magnetic field times my path, which I have here, over the curve S, over the loop S. It has to be a connected curve. This is actually equal to the current that flows through this loop. This is on the other side equal, the current is equal to the surface integral of the current density times here the current density times a normal here dA. This is the Ampere law in integral form. This integral form suffers from many problems. Thinking about relativity, both our loop S has finite dimensions, and on this loop S we put a surface A. This surface A has a normal here 1n. So I have here the magnetic field H. I integrate it around this loop, has to be a closed loop, and I have here, up here, I have my current density J. J, that's a function of coordinates, and this is has the units. J has units of amperes per meter squared. Just I forgot to write the units here, so charge has units ampere seconds, and the electric displacement has units ampere seconds per meter squared. To be on the complete side. Here, the units, what are the units? Magnetic field has the units H, magnetic field H has the units amperes per meter. Current has units amps, and this J I already described it down there. So here there are several problems. So first we need finite dimensions for the integral form. That's a problem with the relativity. Second, in what directions do we go here? Do we go here, or do we go right, or do we go left? This one or this one? Which is right? Again, we need the right-hand rule of the right-handed screw. If I turn it here in the right direction, the screw will go up in the direction of the normal. So a right-handed screw will be here, okay. We also have a problem with English literature. You know that with the magnetic field we have two fields. We have H, field H, that has units amps per meter, and we also have field B that has units volts seconds per meter squared or Tesla. The literature calls both of them magnetic field. Maybe it would be better to call this magnetic field intensity and this thing here magnetic flux density. So to separate between the two, but this is a problem with the units. So we have three problems: finite dimensions, direction, right-handed screw, and we have, in English literature, we have two different quantities that bear the same name. Usually physicists prefer the vector B, electrical engineers prefer the vector H. This is the way it's usually done, but they call them both magnetic field. That's a problem. So now how do we solve the problem in this way, in this case? How do we solve the problem? We solve the problem. So this is here a matter of names, so you have to be careful when you read the textbook, what they are talking about. This problem. The problem of sign here. What is the sign of the magnetic field? Here is this thing is made by convention. This is not given by the physical laws, but rather this is a convention. We decided that we are going to use a right-handed screw. What is behind all this theory? Magnetic field in reality does not exist. This is just a relativistic simplification of our problem so that we don't have to deal with the special theory of relativity. So this sign of vector h should be arbitrary. We have made a convention which sign to use, that one that uses here in the Ampere law the right-handed screw. So this is given by convention. We have to be careful to keep always this convention. It's not that easy as you may think. I regret remembering my physics from the elementary school, where in the textbook we had a proof that magnetic field lines always originate in the north pole of the magnet and also terminate in the south pole of the magnet. After 50 years, I still don't understand that proof. Because it's an arbitrary convention. It's not given to any physical quantities. Why? Because in physics, we don't have magnetic charges. They do not exist in physics. Physicists are looking for them, have been looking for them for many years, but they cannot find them. There are no magnetic charges in the universe. Mathematicians try to make formulas using magnetic charges, but that's mathematicians. Mathematicians don't care about reality. But physicists cannot find magnetic charges. Because there are no magnetic charges, we cannot define this direction here. With electrical quantities, it was not a problem. Electron is negative. That's enough. If we know what an electron is, we know where the arrows do go on this drawing here. All the signs are well defined, just defining one single particle. Because you have a particle that has electric charge and a particle that's well defined. While there are no magnetic particles holding magnetic charges, so acting just like sources or just like sinks of magnetic field lines, the magnetic field lines are always closed loops. We have one final problem, the problem of the finite dimensions. So this integral form, how do we handle that? We can handle that in this way, using the Stokes Theorem in mathematics. What does it say, Stokes Theorem in mathematics? It says that this closed integral along the curve, the loop S, this closed integral on the loop S, it's equal to integral over the surface A, curl of H, times dA. This is the Stokes theorem, and now you see we can compare the Stokes theorem with the Ampere law in integral form. What do we get out? We get the differential form that says that this thing here is identical to the current density here. So curl of H, or density of the vortices of F. This could be said that this is density of vortices of curl. We also write curl in our literature. We write it as curl in this way, rotor H. In English literature, you will see written curl of H. This thing is equal to the current density J. This differential form, what does it do? It shrinks the dimension of our law, Ampere law, down to infinitesimally small. So the differential form doesn't care about the theory of relativity, special theory of relativity. It has no importance here. So we can make all the computations doing exactly here. And where do we have the sign? We know what Nabla is. The sign, we actually have the sign in here. In this cross product. If this is right-handed. If we are calculating the cross product in a right-handed coordinate system, we get the sign correct. So with this here, we fix the sign. So we have yet another formula using talking about magnetic quantities, and the Faraday Law of Induction. What does the Faraday law say? The Faraday law says that the induced voltage in a loop is equal to the derivative of the flux over time. Here I'm a little bit short of letters. Here I'm using the big letter phi for magnetic flux. So the voltage, the induced voltage here has units of volts, and the total magnetic flux has units of there is no ratio of volt seconds. So everything holds up to now. So how do I have the induced voltage inside a loop? So I have a loop here. Here is the induced voltage. I have to think about how much magnetic flux do I have here. The field lines, I draw field lines of this magnetic flux. And the magnetic flux density is the vector B. B that has units of volt seconds per meter squared. So the Faraday law on this side has minus derivative over time. Maybe because I have other coordinates, I should write here partial derivatives now, because I have also other, so partial derivative over time of the integral over surface A. So here I have a surface A that's defined by this loop. This is surface A that has a normal 1n, unit vector 1n, of magnetic flux density B times a normal dA. This is the general Faraday law. On the other side, I could also say that this induced voltage is the integral over this closed loop S, induced electric field dot here is ds, dot this ds, this path where I make this distance I travel along the loop. This could be the complete Faraday law. Now, a little bit of problem is that with this derivative here. This derivative, what it may act upon? It may act upon the vector field B, the magnetic field B, the flux density B. It may act on the size of this surface because this loop may be shrinking or expanding. And it may act on this dot product because the dot product has a cosine. If this loop is rotating in a generator, then this cosine is actually changing. So delta derivative over t may have many meanings. Now, with antennas, we cannot have things that are rotating a million times per second. We cannot do that simply. So we do not have rotation. We do not have loops that shrink 1 million times per second. We only have the magnetic field density that changes. So this is now minus integral over A. I can put the derivative here because this is the only quantity that changes, times normal dA. This is how I kind of rewrite for, so this is general form. And this is no movement. No shrinking, no rotation. So the derivative does not work on the dot, the derivative does not work on A. And this is actually the case with antennas. With antennas, things are very fast, so we cannot have mechanical changes over things. But we should remember where this comes from. Now, how to shrink this thing into a differential form? Again, we make a comparison with the Stokes theorem. We have the Stokes theorem here. We could rewrite this Stokes theorem in this way. So Stokes theorem rewritten here, E dot ds over loop a long loop S is equal the integral over the surface A. The surface A is put on this loop. Curl of E. First we compute the curl times normal dA. And this is the Stokes theorem. How do we rewrite the thing in differential form? So curl of E, the way we want to write it, we can write it also rotor E in our notation, or curl of E in American notation. This is the density of vortices of E is equal here to, should not forget this minus sign, minus B over derivative of B over T, partial derivative B over T. So this is now the differential form. What is now agreed with a convention and what is now fixed? The only thing physics requires is that the Ampere law and the Faraday law have different signs. Here the signs are different. Here's a plus sign, here's a minus sign. And that's all what requires. So plus sign here, minus sign here. Nothing else. Now that we choose, these two signs should be different, but by convention, we are taking this convention is putting a plus sign here. This is by convention for a right-handed system, and puts a minus sign here. This is everything that's needed, or this minus sign here, or this minus sign here. In this way, we define the sign of the magnetic quantities that are not real, that are just our simplification of the theory of relativity. That's all what we have. Now, in order to have the complete equations, we should also think about what is this J here. So if I write here curl of A, curl of H, this is the total current J, total current density. But this current density in physical problems may take different forms. This current is actually J conductive. Conductive current, we have conductive current in metals. So negative electrons are moved in a positive lattice. That's the reason why the total charge is 0, but we have some conductive current in metals. We may have convective currents in vacuum, like in vacuum tube. That we have electrons moving in vacuum. We have convective current. Convective current is much slower than conductive current. Conductive current has the speed of light. Convective current is much, way slower. A simple explanation what is conductive and what is convective is your garden hose to water your garden. If your hose is full of water, then when you open the water, water immediately flows on out on the other end. So that difference in pressure actually travels at the speed of sound in water. That's 1.5 kilometers per second. But if your garden hose is empty, it takes some time because before this hose fills with water and water starts flowing on the other end. So starting with an empty hose, we have a convective current of water that may take lots of time, maybe just a few meters per second, in place of the 1.5 kilometers per second to reach the other end. So we have this in metals. Vacuum tubes. That's the reason why vacuum tubes are sloped. Also in semiconductors, we also have conductive currents, not just of electrons, also of holes. And they also have a quite limited vacuum tubes semiconductors. And finally, we have a displacement current. So if I draw here, if this is the source, I can have a resistor that has a conductive current. I can have a vacuum tube that has electrons flowing in the other direction. That's convective current. And I may have a capacitor that's charging. So I have conductive tube in the metals of the resistor. In vacuum tube, I have convective currents of the electrons. And I have displacement current here. The displacement current is now the change of the displacement field over time. So this is really an extension of the Ampere law. Ampere just stated that we have current here. We have to define more precisely what that current is. Now, to conclude, to put all these equations together, what do we get? We get, first we write this first equation, the Ampere law. The Ampere law is curl or density of vortices of magnetic field intensity is here. With the letter J now with no suffixes, we mean conductive current. Convective current, we are not going to solve our equation in semiconductors, so this is just conductive current, but we have to think about the displacement field. We have the induction, so curl of electric field is equal to minus, by convention, minus derivative of the field B, magnetic field intensity over time. And finally, the third law, we have the Gaussian law. The Gaussian law, so divergence of the electric displacement is equal to the charge density. These are Maxwell equations in time domain. What happens if I will use this figure here, just changing the color. What happens if I calculate the divergence of this thing? If we have a triple product on this side with two identical vectors, this thing is 0. The divergence of a field of vortices is always equal to 0. So you have 0 is equal divergence of the derivative of B over time. Or this simply means that the divergence of the vector B is always equal to 0. If its derivative is equal to 0, it can never change, so it has to be 0. If I calculate the divergence on the second Maxwell equation, I simply see that there are no magnetic charges. So this could be magnetic charges. Say I call it raw magnetic. Magnetic charges are always equal to 0. There are no sources of magnetic field. There are no magnetic charges. This is simply told by the second Maxwell equation. But physicists are still looking for these charges, but they cannot find them. That was in time domain. We frequently write our equations in frequency domain, and Maxwell equations hold everywhere. In free space, they hold in conductors as well. So I have to see what form do they take in different problems, in different fields. So in vacuum, what we have? We have the electrical displacement is equal the permittivity of free space times the electric field. And this permittivity in this case is a scalar, is not a tensor. And the magnetic field density is equal to the permeability of free space times vector H times magnetic field intensity. If I'm accurate and I'm using two different names for B and H. And in vacuum, there is no conductive current. We may have convective current, but the conductive current I'm using now the symbol J just for conductive current. So this is just conductive here. J total could be right here. But in any matter, I can have different relationship. The electric displacement is permittivity of free space times a relative permittivity of the matter we have times electric field E. And this relative permittivity may be a tensor. Matter may be non-isotropic. A typical non-isotropic example is the fiberglass epoxy laminate used for printed circuit boards. So it's not something we do not see in our life. We have plenty of printed circuit boards in our life. The magnetic flux density is permeability of free space times relative permeability of the material times magnetic field intensity, or magnetizing field H, also called in English. And in matter, we have conductive current, that's conductivity times electric field E. So using these things for vacuum and these things for matter, we could rewrite the Maxwell equations in this way. So further, well, I'm going first to rewrite them. So curl of magnetic field intensity is now could be conductivity times conductivity times field E, plus here we have permittivity, maybe of free space. I'm just going to write the permittivity just as a single letter epsilon. So single letter epsilon. So epsilon is epsilon 0 times epsilon relative for the permittivities. And mu is also mu 0 times mu relative to keep the equation simple. Times the derivative of electric field over time. And the curl of the electric field is now minus sign here, derivative mu, so permeability of the matter, times the derivative of H over T. In this way, I reduce the number of variables here. Here I have had 1, 2, 3, 4, 5, 6 independent variables. If I want to solve the equations, I have to replace all these things to keep things simple. And there is little difference to the Gauss equation. So the curl of E, no longer D, no longer displacement, but electric field, is now rho over permittivity. So introducing vacuum or matter cuts down the number of variables I have here. Here I also prefer to write J, so here can be also J in place of this thing here. Could be also J. Now one final simplification of the Maxwell equations is we go to frequency domain. Using phasors for our quantities. All our quantities are complex quantities, are phasors. So calculating things with phasors simplifies the derivatives. So in frequency domain, if we have a frequency omega, a harmonic example of frequency omega, the derivative over time is simply replaced by j omega. And that simplifies because multiplying things is much easier than derivating something. So, but we have to remember that all quantities are now phasors. They are complex numbers. So the curl of H, we can also compute the curl on complex quantities, that's not a problem, is now current density J plus here J omega epsilon electric field. So the derivative is replaced by j omega. The Faraday law is now a curl of electric field. Is now minus, because of the j omega mu h. And the final, this has no time derivative, so the Gauss equation stays the same. The Gauss equation stays as it was, is equal to rho over epsilon. This is rewriting the Maxwell equations now for matter and rewriting Maxwell equations for in the frequency domain. And this is what we actually are going to use. Now you may argue, as you heard with the fundamentals, that relative permeability of some materials like iron may be highly nonlinear. Well, at high frequencies where we build antennas, matter is almost perfectly linear, so we don't see this nonlinearity, and we can use these simple equations. Of course, if we are going down building electrical machines for a power station operating at 50 Hertz, then we should take account of this nonlinearity, and equations are no longer linear. These equations for antennas are always linear. So what will be our first problem next hour? Our first problem will be find, given the fields, given, find the unknowns. What unknowns do we have here? The unknowns are the magnetic field and the electric field. We have three equations to find out two vector fields. So this is unknown. And that's our basic problem. We know where we have currents, we know where we have charges. Now we want to find what is the field generated by these currents, by these charges. And this is the simplest problem we can think of with antennas. We have more difficult problems also with antennas. But this is a simple problem, simple thing we have to find out next hour.